guys, hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. I'd like to welcome each and every one of us into my discussion for today. I'm going to look at a concept of loci in the Argand diagram. Now, we have come across this specific term in our previous discussion on the concept of graphing, and we're going to see that particularly graphing of different functions, and we're going to see that this is going to be one of the applications whereby we are going to borrow from inequalities and equalities of equations and a representation of particularly this specific phase of the complex numbers in terms of the Argand diagram. Now, in this specific case, we shall look at a way of finding this specific representation for the option of 1, 2, 3, and 4 respectively. And in this case, we will consider this one to be represented as the normal equations which we have been doing for the concept of graphing. And then for the last one, we shall look at the concept of an argument of the phase of Z. And this is going to be forming basically the summary of our particularly representation of different loci which we may come across in form of or in the Argand diagram in this specific case. So we are going to consider a set of points which are going to be in form of these specific options which I have given. And in the first case, we shall look at the magnitude of the phase of Z plus 2, which is smaller than or equivalent to the complex conjugate of Z given as such. And this is going to be giving us within the limits of this angle, which we have given for 90 and 180 degrees for the phase of Z. Now, for the second one, we're as well going to look at basically the magnitude of this phase of Z, which is going to be ranging between 1 and 2. And this is going to be the magnitude of Z, which is equivalent to or smaller than 2. And lastly, this is specific argument which I've basically given. Now, in this case, we'll consider having this solution of the first option being given as such. So we are going to have the phase of Z plus 2, the magnitude of this specific set, and we shall have the complex conjugate, the magnitude of the complex conjugate of this specific phase given as such. So this is equivalent to, or can be given in terms of a representation of this specific phase of Z, whereby we had said that we can represent this set in terms of this rectangular, of course, or we can represent it in terms of x and y, whereby we're going to have a real component and imaginary unit, and of course this whole set is going to be forming of course an imaginary component of this phase of Z, and therefore this is going to be represented in form of a substitution of this specific of course representation for the first case. So we shall have this one given in terms of the phase of Z, which is going to be basically given in terms of x plus the imaginary unit and I, and this is going to be given with a sum over 2. So therefore this is going to be representing the magnitude for the left side of this specific equation, and we shall have that one equivalent to the magnitude of the complex conjugate of this specific phase. So we're going to represent this complex conjugate in terms of x plus, so basically this is going to be a negative x minus the imaginary unit, and we're going to find of course the magnitude of that. So this is going to be basically represented by this particular equation, and therefore we go ahead and try to find a particular evaluation for this equation which we have given in terms of x I y plus 2. So we shall have this one given as such plus 2, and then we're going to have the magnitude of that is smaller than or equivalent to of course the imaginary unit, and of course y given as such. So what we shall do is basically trying to find this specific aspect of magnitude, whereby we are going to see that for us to find the magnitude, just as we had been doing for this specific equation, we'll have a square of these specific terms which we are going to have as such. So we can do a rearrangement by finding the real terms of this specific first set of magnitude by having the sum of x plus 2, and this is going to be given in terms of the components of this y and 2, of course x and 2, which are going to be forming the real parts. So we shall have a square of this specific first set of magnitude plus the magnitude of this y component given as y squared, and this is going to be given as, so we shall have solved for the magnitude of the first set of equations which was forming the left side of the equation, and we will have a magnitude of the second part given in terms of the square over x and the square of y given as such. So we'll have solved for this particular set of magnitude for the left and right side of the equation, And this is going to be giving us such a kind of an equation as the one which I've basically illustrated on board. So for this kind of a squares, we're going to have x, the square of x plus 4x plus 4 given as such. And of course, we're going to have this one plus y for the left side of the equation, and then we shall have this one equivalent to or smaller than. Of course, this other side of the equation is going to be just retained. So we shall have this one given in terms of that specific representation. So if we try to look at this specific case, we are going to have the term of x squared and y squared being represented on both sides of the equation. And therefore, we'll just do a rearrangement for us to obtain this specific term, which is going to be given in terms of 4x, which is going to be smaller than or equivalent to. So we're going to take this specific aspect of 4, which is a numerical number, to the other side of the equation, and it's going to be forming our negative 4. So we will have the particular value of x either smaller than or equivalent to the value of negative 1. And this, of course, will be giving us that specific line that we are going to consider in trying to represent this specific kind of course, what we refer to as a loci. So in this case, we are going to have this one represented in the Argand diagram, particularly for considering this specific evaluation which we have found for the value of x, which is of course smaller than or equivalent to negative 1. So in this case, I'll just have this one given as such. So we're going to have this one represented as the value of x is of course smaller than or equivalent to the value of negative 1 given as such. And we're going to have this specific representation for the Argand diagram given as. So we are going to have this specific representation for the Argand diagram, whereby we're going to have this real component of that complex number, and we're going to have the imaginary component of these complex numbers given as such. So in this case, at this specific point, we're going to be having positive 1, 2, 3 given as such, negative 1, negative 2. So this is going to be along the opposite side of the real, of course, component given as such, which is going to be, of course, the axis of z, z which can be given in terms of, as we said, xy. If we are going to consider the xy components, then we're going to see that x is going to be representing the real part, which can be given as such, and we're going to have this one given in terms of those specific, of course, demarcations for negative and positive given as such. So for us to find this specific representation, which is going to be giving us a value at negative 1, we're going to have a specific range of values which are going to be, of course, representing x, which is either equivalent to or smaller than negative 1. And this is going to be constituting a region which is going to be the region beyond this specific part. And of course, this is going to be either represented as equivalent to or perhaps, of course, equivalent to or perhaps greater than, which is going to be greater than x. So therefore, we are going to consider this specific region which I've just left, which is going to be unshaded, and that is going to be representing that specific, of course, inequality which I've, or this specific, of course, set of points which I've just given on the board. Now, in this particular case, we're also going to consider this specific case for the range of values, whereby we are going to have this particular set of restriction which we have been given between, whereby the set of angles are going to be represented between this particular phasor, which is going to be between 90 and 180 degrees. So these are going to be considered from this specific range of angles, whereby we're going to have this specific, of course, angle being measured towards the, of course, anti-clockwise direction. And this is going to be representing a value of pi all over 2 and pi given at this specific point. So therefore, we are going to consider this specific region which is going to be restricted within, of course, this specific region of pi, which is 180 degrees. And this is going to be forming this specific region which basically we have marked on the board given as such. So that's going to be forming our first option for the representation of that specific set of points. And as well, we are going to consider the case whereby we're going to see that if we take these specific values of the second case, which is going to be giving us that specific magnitude for the phase of z, we can as well represent it in the Argand diagram by having this particular representation which we are going to have as such. So we shall have this one in terms of option 2, which is going to be 1 is smaller than or equivalent to the magnitude of the phase of z given as 2. And if we try to look at this, we can as well have the graph of this specific function by considering the Argand diagram for this specific, of course, set of points. So we shall have 1, 2, and 3 given as such, -1, -2, and then 1, 2 given as such, 1, 2, 3 perhaps given as such. So it's going to be the real components represented as such and the imaginary component of z given as such. So these are going to be forming negative values. So for the first case, we're going to see that we can consider the phasor magnitude of the phase of z, of course, being equivalent to or greater than 1. So we're going to have this specific region denoted as such, which is going to be forming our set of points which are going to be, of course, outside this specific boundary which I've just shaded. And therefore, the phase of z is going to be represented as this specific section of the equation using this specific representation. Now, if we consider the second case whereby the phase of z is going to be equivalent to or smaller than 2, and therefore that's going to form another set of points which we are going to consider for the second case, which is going to be a region whereby 2 is greater than, for that specific magnitude, 2 is greater than this specific point. So therefore, this is going to be forming this region which we are going to consider for the set of points which I've just given on the board. And that's going to be another representation we can, of course, check for this specific option for number 2. So we are going to consider the option number 3 and try to see how we can represent this set of points on the Argand diagram. So this as well is going to be a representation on the, of course, Argand diagram using these two specific components which I've said for real and imaginary. So we are going to consider the case of the magnitude of z, which is smaller than or equivalent to 2. So basically, we are going to have this specific set of points for the value of negative and positive 2 given as such. And this is going to be a region bounded by this specific point, whereby we are going to see that this specific value is going to be defined by a set of points which are going to be 2 is going to be greater, so they are going to be smaller than 2. And this is going to be the region defined by this specific set of points given as such. Now we're going to look at the last option, which is going to be assisting us try to give a representation of that specific argument of z. And we're going to have that one as well represented in terms of this Argand diagram. So we shall have this one given as such, whereby we're going to have this imaginary component and the real component given as such. Now the argument is going to be given between this specific set of values for the negative pi all over 3, and the argument is going to be given in terms of either smaller than or equivalent to, of course, pi all over 2. So these are going to form a range of, we have seen how we can represent angles in terms of pi or radians or degrees. So this basically is equivalent to 60 degrees if we can just have that specific conversion. And this is going to be equivalent to 90 degrees. So we're going to consider the upper part of this specific, or the upper region of this specific angle to be, of course, a restriction of pi all over 2 degrees. And this is going to be defined by this specific region, which we are going to consider for the positive part of this specific angle. And this is going to be the anti-clockwise direction for the positive pi all over 2 given as such. Now, the second case, we're going to have this argument restricted as well within this specific set of angles for the negative. So we're going to see that the clockwise direction of specific angles extended from this, of course, x, or the real axis, is going to be defined as a negative. And this is going to be making up an extension, a subtension of 60 degrees. So we shall have this specific region defined between this and pi, negative pi all over 3 given as such. And this is going to be the region which we are going to be after, which is going to be defined by this particular argument of z, which we have given in terms of this specific set of points. So that's going to be forming our final bit of this specific discussion on the concept of Loci in the Argand diagram. and we're going to come across various range of examples which are going to be assisting us try to, of course, evaluate other problem sets which we are going to come across. So that is it for now, guys. Bye, God bless you. Catch us in our next video.